Good morning, everyone. My name is Ray Alvarez Parmar. I'm a solutions architect at AWS, and today I have with me Ila.
Hello, everyone. Myself, Ilamaran Shanmugam. I go by Ila. I'm a senior container specialist SA with AWS.
So as you can tell by the title, we're here to talk about workloads. So the first two talks were focused on product and engineering and how the EKS teams run the back-end control planes. We're going to talk a lot about what you can do. So this is to improve the availability and the reliability and resilience of the applications that you build on top of EKS. So one of the design principles that we have at AWS whenever we're creating software or any product is we assume the worst. We design for failure. And a lot of engineering effort goes into making sure that our products are developed in a way that they are highly available, that they're fault tolerant, and it allows us to continuously update our products without bringing your clusters down. So as SAs, our job is to talk to customers, and we talk to a lot of customers that are running EKS at scale. And when we are in these conversations, a lot of questions that we get asked are about how can customers build applications that are really highly available and resilient. So some design principles that we talk about. One of the primary things when you're building architecture is that you have to make sure that your applications are highly available, that you don't have single points of failure. Your applications need to be fault tolerant, so that they should be able to sustain some amount of failure in individual components that you may be running. Your applications need to be able to scale automatically, so as you get more traffic or the workload pressure increases, you should be able to scale your applications in a way that you're able to now support a lot more than what you were doing maybe an hour ago. And then similarly scale back down to ensure that you're not using a lot of resources. And then self-healing, your applications need to expose internal metrics so that something external to your application can observe how your application is performing and then heal it when something goes wrong. So if you have a deadlock, or if you're running out of memory, or if your process gets killed because you have an out-of-memory error, you should be able to expose that to an external entity that can then detect it and correct that failure. And then since we are all living in CI/CD world, modern applications need to have a way to be able to be constantly updated. You can't just install a piece of software every 6 months. That's not the frame anymore. You need to make sure that you're able to update that software that you deploy, and you deploy it in such a way that if things go wrong, you're able to roll back, or hopefully you can do things like automatic rollbacks. So the good news is that if you're using Kubernetes, you're kind of 50% there already, because Kubernetes gives you this abstraction that allows you to run software in a way that can be highly available, that can be fault tolerant, that can make sure that you can make sure that it scales. So things like deployments, for example. If you're using deployments to create your pods, you can ensure that when an individual pod fails, Kubernetes will recreate a pod and you won't have a software failure. Similarly, things like horizontal pod autoscaler. So if you're using horizontal pod autoscaler, you can plug that into metrics. You can include CPU memory metrics, or you can use external metrics to make sure that your application scales as you receive more traffic, or if you increase memory, or if the CPU usage goes up, you can automatically scale your applications. And then underlying things like infrastructure, like nodes. Kubernetes has Carpenter and Cluster Autoscaler that will give you a way to scale your data plane as your workload scales. So you don't have to anymore worry about managing the auto-scaling groups or making sure that you have enough capacity in your cluster. Kubernetes does that for you. And then the EKS managed node groups really make it easy for you to maintain the life cycle of your workload, including the underlying data plane. So managed node groups really give you this really easy way to create nodes, to update nodes, and managed node groups does automate a lot of what operations people will have to do. For example, monitoring the health of an individual node, replacing a node, and scaling your node groups. So if you're using Kubernetes, you're kind of already there All you have to do is now use the actual underlying constructs to make sure that your application that you're deploying follows some of the best practices that Kubernetes has. So this is a view of the EKS control plane. Many of you may have seen this, but the way we deploy an individual control plane is highly available and fault tolerant. So we deploy the API server across three availability zones. And the way we deploy it makes sure that if there's a failure in one of the individual availability zones, your cluster will not get affected. So if one of the API server fails, your applications are still up and running, your cluster is still up and running, and you can make changes to your cluster without getting disrupted. Similarly, for the etcd cluster that we create, individual nodes in etcd can fail, but that would not affect the operation of your entire cluster. So EKS has this shared responsibility model where you're responsible for the workload that you're deploying in EKS. You are responsible for the EC2 nodes, but you're not responsible for the cluster control plane. Things like kube scheduler, things like etcd cluster, they're not your responsibility. So that EKS assumes the responsibility of managing and updating and securing the control plane itself, while you can focus really on the workload. And if you look on the left-hand side, if you use Fargate, you offload even more functionality to AWS. Because in Fargate, you can really create your containers and tell Fargate to run your containers. So you don't have to do things like creating armies or managing node groups or upgrading the add-ons for kubeproxy and the CNI. Fargate will manage that for you. So for customers that are looking to decrease their operational burden, Fargate is a very optimal solution. Just a very quick update. We run a lot of clusters for customers. I think the number Jody talked about was we run millions of nodes and thousands of clusters. So we have a lot of experience that we learned. And as part of that, we're constantly evolving the cluster control plane. So just last year, we made some improvements to the provisioning and update procedure of how we update the control plane. So now we've decreased the time that it takes for you to create a new cluster control plane or update it. So things like we're now doing faster API and etcd cluster scaling. We're also doing blue-green deployments. Previously, we used to upgrade your cluster in a way that we used to do it like almost like a rolling update, but now we're doing blue-green upgrade, which really makes it faster for you to upgrade that time, because as you may know that when you're upgrading a cluster, you're not unable to make changes to the cluster until the upgrade is completed. So by reducing this time, we're ensuring that whenever there are operations that you need to do within the cluster, you don't have to get delayed on that. Okay, so what are some of the things that you can do in your workloads running in Kubernetes? So one of the core things that we talk about is make sure that whenever you're deploying your applications, you're deploying in such a way that it follows the Kubernetes best practices. So whenever possible, you should use Kubernetes self-healing mechanisms so that you're not the one that's monitoring your application and restarting in the middle of night when it crashes. So use things like deployments. If you're deploying containers as pods, don't do that. Use deployments, because if your pod fails, deployments will recreate a pod for you. And then you can also do things like horizontal pod auto-scaling with deployments. Another thing that we talk about to customers is make sure that for critical applications, you're not putting all the pods on the same node. So use things like anti-affinity, pod anti-affinity, and spread nodes and pods across multiple availability zones. Because you should assume that at some point, one of the AZs may go, at any point, one of the AZs may go down. So what is going to be that strategy that you're going to use to make sure that your application doesn't get affected when there's a failure in the AZ? And then use health checks and probes. So Kubernetes has a really cool way of detecting the health of your application. So use that. I recommend do not deploy any application in production without having a health check strategy. So you allow Kubernetes to be the SRE for you instead of someone sitting there watching your application and restarting when it fails. In multi-tenant environments, use quotas and limits. We're seeing a lot of customers run very, very large clusters because they'd like to consolidate. No one wants to run hundreds of clusters. If possible, companies want to maybe operate a couple of clusters to diversify, but running a large amount of cluster is a lot of operational overhead. So we're seeing many people use 1 or 2 clusters for the entire company. That could be a recipe for failure if you don't have a plan. And Kubernetes, fortunately, offers things like resource quotas, namespace limits, and isolation tools, so you can make sure that one of the tenants in your cluster doesn't end up breaking the cluster for the rest of the tenants. So use resource quotas, namespace limits, put a limit on everything. Assume that there's going to be someone that is going to create resources and end up taking all the resources in your cluster. So just always go with that assumption. Another thing that we recommend is GitOps. GitOps is a really cool way because instead of making changes, imperative changes into the cluster, you can make changes through a Git pipeline, and then it gives you the ability to track what you're doing, but it also gives you an ability of having a record of everything that you changed. And then at any point your cluster gets compromised or you need to recreate in a cluster, now you have the entire configuration set sitting in a Git repository. So we've seen customers spin up clusters, production clusters or replicate clusters using GitOps within a matter of hours. And doing the same thing otherwise would take probably days. So use GitOps whenever possible. It gives you a mechanism to do code checks, code reviews, approve changes, deny changes. So as much as possible, don't make changes directly into the Kubernetes cluster. Use GitOps or some kind of CI pipeline to do it. And then monitor your applications, but also monitor Kubernetes control plane, Kubernetes data plane resources like core DNS and kubeproxy. I can't tell you how many conversations I've had with customers where they were scaling and had a problem with core DNS. And core DNS often becomes a choke point, so it's very important for you to monitor the DNS latency so your application is not failing. And one of the key things that we see customers running into when they're scaling cluster is DNS not operating, and which leads to this cascading failures across clusters. So make sure that you're monitoring these components that you may not be thinking of today, because whenever we're deploying applications, we're just thinking of the application itself. But also think of what are the add-ons that you're running, what are the other components that you also need to monitor. And then wherever possible, use EKS add-ons. So EKS add-ons, if you have not tried it yet, it's super cool because one of the things that you have to continuously do in EKS is update add-ons, because Kubernetes upstream community is constantly releasing new updates. And it may be hard for you to know when to update core DNS, when to update kubeproxy. EKS makes it really easy for you because if you're in the dashboard, you'll see a notification right there that there is an update available. And all you have to do is go click the update button or use the API to actually make the update. So really easy thing for you to improve the availability and also the security of your cluster. Some of the other things to talk about is, especially as you grow, each AWS account comes with some default limits for the services that you can use. So for example, in a default account, you may be limited in the number of EC2 instances that you can create. You're also limited in the number of API calls that you can make per second. So as you grow your account, you may be hitting closer to that quota. So first thing is know where your quotas are. There's an easy way to find out in the console or through CLI where you can see where your account is in terms of that quota, and then keep a track of it and know what percent utilization you're at, so you can request a limit increase when you need to scale up. Monitor things like network. So CNI is super important. As you know, in EKS, if you don't have IP addresses, you're not going to be able to create pods. So here's another problem that many customers run into is they would create a cluster, and then at some point all the pods are pending. The reason may be that you don't have enough IP addresses. So you can use CNI Metrics Helper, which is a really cool tool that they'll create you a CloudWatch dashboard, and you can create an alarm and say if the number of IP addresses is below 20, then do something, like send you a message or send you a Slack message, something like that, so you can get alerted and act upon it. You don't want to wait until you don't want to wait when your network, when your subnet is already out of IP addresses, because that could cause outage in some cases. Another thing that we see, especially in larger clusters, is controllers. Controllers may put a lot of pressure on the API server, especially things like FluentBit, FluentD, things like Prometheus. Many controllers that scrape metadata from the API server, what ends up happening is if you have, let's say you have a lot of daemon sets and you have thousands of nodes running, all of those daemon sets are constantly going to the API server and say, give me new pods, give me new nodes, and that could put a lot of pressure on the API server. So we're seeing customers where they run into these situations where the API server is so slow that you can't scale, you can't create deployments, you can't even create config maps. So wherever possible, try to use controllers that allow you to scrape metadata from kubelet instead of the control plane. So like FluentBit has this feature where you can point it to use the kubelet to discover pods on the node instead of going to the API server. So that significantly reduces the amount of pressure that you put on the API server itself. And then for production clusters, have control plane logging. Because if you don't have control plane log, and if you have an error or if you have a problem with the cluster, you wouldn't be able to know what went wrong if you don't have the logs. And one of the cool things that you can do with control plane logging is all the control plane logs get sent to CloudWatch. And CloudWatch has this really cool feature called Log Insights, where you can create queries like this and find out analyze your logs, your control plane logs. So for example, here I have a query that you can run to find out what are the controllers that are making calls to those API servers. So for example, here I can see that my REST client is making the most calls. So this is a good way if you're experiencing latency and if you want to know which controller is really sending most traffic. You can enable the logs, and you can then use CloudWatch Log Insights to create a query like this. And then once you're all set, once you know that you've configured your application in a way that is very reliable, very resilient, you should test it. Because unless you test it, you wouldn't know how reliable your application is. And so AWS Fault Injection Simulator is a service that allows you to artificially introduce chaos in your cluster. And it includes some really easy to use templates that you can use. You don't have to have an experience in writing a lot of code or templates. You can reuse the templates provided by the Injection Simulator to inject failure into your cluster. For example, you can increase the stress of a CPU in a pod. You can terminate nodes at random. You could go and increase latency between nodes. So there are some templates available that will get you started. And one of the really cool things is it's chaos fault injection simulator doesn't just create a fault in your cluster and goes away. It has a rules engine that you can set up and say, start this test, but if a condition is met where you may say that if my application is offline or if my application latency increases, then stop the test right away. So you don't have to be also monitoring once the simulation injector starts working. It has a detection mechanism that you can use to stop the test as well. Having said that, I don't think anyone is going to say that Kubernetes is fault-proof. There have been situations where even the best well-architected clusters have failed. I don't think there's any shortage of those stories. So what we're seeing is that we have customers that are now coming to us and asking, how do I ensure against a configuration error? I've had situations where a giant cluster got brought down because someone changed the CNI and all the nodes went offline. So now customers are coming to us and say, give us a strategy that we can use to ensure against failures like that. How do we make sure that when a configuration change happens, the cluster doesn't go offline? Or how do we make sure that a faulty controller is not going to compromise our production environment? Or how do we make sure that when we upgrade our cluster, the next API version is going to be 100% compatible with our workload? So what we're seeing is a lot of customers are considering multi-cluster strategy. So one of the things that the reasons that customers are thinking of multi-cluster is, let's be clear, like there's a lot of confusion on why should you go multi-cluster. So here are the key reasons why you want to go multi-cluster. Most of the time, customers want to go multi-cluster because they don't want to have a single point of failure. Kubernetes, one Kubernetes cluster that's so big that it's too big to fail. So in order to avoid that kind of scenario, now customers are thinking of creating multiple clusters so that if one of them fails, well, you still have another one available. Doing things like blue-green upgrades, so not only just cluster upgrades, but also application upgrades. In some scenarios, you may not want to update the application in your main cluster. You might want to try it out first in a secondary cluster. So that's where we're seeing customers thinking of running multiple clusters so that they can change one stack and keep the rest stack easy, and do things like A/B testing. So when you have to do things like that, because your two clusters in this environment have to look identical, there are some key requirements that you need to set up. So whenever you're thinking of doing multi-cluster, you need to make sure that some of these key requirements are met. So for example, one of them is that you have to have consistent deployment across multiple clusters. That includes the cluster configuration and application deployment. So whenever we're talking to customers about running multiple clusters, no one wants to run two different clusters because that's just too much operational pain. So you need to have a strategy of making sure that you're deploying consistently across the two clusters. Then, because most of these workloads receive traffic from external sources, and you want to do canary and A/B testing scenario, you need to make sure that you have a way to distribute traffic across those two clusters. So that's a very key important piece. And then you also need the ability to remove any of these clusters when things go wrong. So if your deployment doesn't go as planned, you should be able to quickly take a cluster out of rotation, fix it, and then put it back in. So in the next section, we're going to focus on multi-cluster configuration, and Eli is going to talk about that.
Thank you, Ray. So Ray did cover a lot of ground on running single Kubernetes clusters, and he also covered about some requirements to run multiple Kubernetes clusters. So let's zoom in on each of these requirements. So let's zoom in on each of these requirements and talk about some best practices here. So first and foremost is GitOps. So what is GitOps? GitOps is fundamentally a mechanism where you use a single monorepo or a single repo. You keep your cluster configurations, and you're going to use that as an approach to deploy those cluster configurations across your clusters and your application deployment configurations across clusters, right? So which means you're going to have a single source of truth to deploy configurations across your clusters. So we have seen so many customers using GitOps as an approach is just because it is going to help you to prevent, detect, and remediate any misconfigurations. Let's say if there is a faulty controller, if the cluster is going down, you can use GitOps as an approach to bring a new cluster and keep a consistency in terms of your configurations. So GitOps is one approach we have seen customers using for consistency in terms of configurations. Let's zoom in a little bit on GitOps with a sample architecture. Let's take an architecture where we are having two EKS clusters. We have installed GitOps on that particular cluster. Opinionatedly, you can use Flex or Argo CD. So what's happening here is we are having a single cluster where we are going to sync that single repo to multiple clusters. So the cluster is synced and the configurations are synced across multiple clusters. So let's say an ops persona comes and says that, hey, I want to change one of the configurations on both the clusters. So what he's going to do is he's going to just make the change, commit his change to the Git repo, and then submit a pull request. So the lead guy in the organization is going to take the change, review the change, and approve the pull request. So once the pull request is approved, so what's going to happen is the cluster sync process takes kickoff, and then obviously it's going to kick off that particular configuration syncing across both the clusters. So which means that you're going to bring in a single monorepo approach to sync your cluster configurations across multitudes of EKS clusters. So we have seen customers doing this, so we highly recommend this approach when you want to keep consistency across multiple clusters. So that's with respect to the first requirement which Ray was talking about. Let's zoom in a little bit about traffic routing, the fun part, right? So we constantly get questions from customers on, hey, I have 2 clusters. How am I going to route traffic? What is the pattern I need to use? I have layer 4 load balancing. I have layer 7 load balancing requirements. So how do I do that, right? So we're going to see some 3 best practices that we recommend to customers in terms of traffic routing. The first situation is a dedicated ALB. So we have seen customers, they say that, hey, I wanted a dedicated application load balancer across my clusters, right? So you can run a multi-zone cluster or you can run a single zone cluster. It's up to the business need. But fundamentally, the aspect here is that we wanted the cluster creation, the ALB creation process as part of the cluster, right? You can use controllers like ALB load balancer controller. So whenever you're creating an ingress resource for one of your services, it's going to automatically create an application load balancer. So which means that each of your cluster is having its own application load balancer, and the application load balancer's lifecycle is managed by the cluster, the day-to operational tooling in the cluster. So obviously, when you're going to route the traffic, Route 53 is going to help us doing the weighted routing across both the ALPs. So one caveat with this approach is that you're going to have one ALB per cluster, which means you're going to introduce cost in terms of multiple ALBs. So that is dedicated ALB approach, but in order to overcome the shortfall of this approach, we have a next approach, which is called shared ALB. So in this approach, what we are doing here is we are keeping the ALB creation process outside of the cluster's lifecycle, which means the ALB is created outside of the cluster process. So which means that you're using the same application load balancer across multitudes of clusters. So in this approach, we're going to use Route 53. Route 53 is going to take care of sending the traffic to the ALB, and application load balancer is going to take care of routing the traffic across the services in 2 EKS clusters. So one thing that we have to note here is that this uses the concept of target group binding. So what happens is when you're creating your ALB, you put on 2 weights across the 2 targets, across the 2 clusters, and you can determine the weight, right? Let's say you can keep 50-50 weight, or you can keep 90-10 weight. You can do kind of an A/B testing here as well in this approach. So fundamentally, that's with respect to shared ALB. But we have seen so many customers talking about layer 4 load balancing, right? For example, we have seen customers, they want to use Nginx controller, or they have told us that we want to terminate the traffic directly on the pod. So in that situations, application load balancer is not a viable solution, right? So in that case, we're going to use network load balancer. So with network load balancer, you can terminate the traffic directly on the pod, which is running the workload. And then obviously you can use controllers like ALB ingress controller, which in terms takes care of managing the life cycle of the network load balancer. So which means that we are keeping the process of creating the network load balancer's life cycle within the Kubernetes cluster. And then obviously the caveat here is how we are going to load balance the traffic across the 2 network load balancers. So that is where we can use services like Global Accelerator. Global Accelerator has a mechanism of weighted routing. So which means that it's going to do the weights and it's going to route the traffic across 2 different network load balances that is pointing to the 2 EKS clusters. So with these 3 approaches, you can definitely determine one of the approaches that is required for your organization's network routing across multiple EKS clusters. All right. So next let's talk about some fun part, right? So how am I going to run multi-region, multiple Kubernetes cluster? So before we talk about some of the practices and some of the tricks that we can accomplish or use in doing this, let's talk about why customers want to run multiple clusters. The first and foremost is disaster recovery, right? So let's say you're running active passive, your workloads is running in a single cluster. Let's say there is a regional failure for some reasons, right? You wanted to have a mechanism where you can do a backup and recovery and run your workloads quickly on the second region. So that is a fundamental reason why customers choose to use multi-cluster, basically disaster recovery. The second important thing is, let's say a mission critical workload, or you wanted to have your workloads close to your users who are geographically separated, right? So you want to run active patterns across multiple regions. And that is where customers do like to run their workloads in multiple regions. But also remember that most of the customers still run their clusters in single region. I'll just tell you why. So running multi-region is going to introduce a lot of challenges, right? The first and foremost is data and database replication. So let's say your container workloads are using persistent volumes. How are you going to replicate the data from one region A to region B? How are you going to accommodate for the replication lag, right? So that's a fundamental thing. And then database replication. Let's say you're having a database and your workloads are spanning across two regions, or doing an active passive, whatever is a strategy or an architecture you're following. How are you going to replicate the data? How are you going to accommodate for the replication lag when you're having a single writer database, right? So that's another problem you need to solve when you're doing multi-region. The third important thing is, even if you're using GitOps, I was talking about GitOps where you can use consistency in terms of deploying across multiple clusters. Even if you're using GitOps, when you're doing multi-region, some of the configurations are going to be region specific. So which means that there is a possibility that you're going to run into regional configuration drift in terms of regions. So how are you going to accommodate that? And the fourth important thing is operational complexity. Two regions, two sets of DevOps, two sets of operational tooling. How are you going to observe two environments? How are your operational personas going to take care of running the operations in two different regions? So that's another challenge we need to account for when you're running multi-region. And the final thing is, of course, the thing that we all worry about is cost, right? Talking about data transfer cost across two regions, talking about maintaining infrastructure in two regions, talking about running operational tooling in two regions. All of those things are going to be pretty cost intensive, right? So talking about multi-region, these are some of the challenges, not limited to, but we need to address when you're having a better architecture or the best architecture for your organization. So, but we are not going to leave here. We're going to talk about some of the best practices you can follow to achieve or accommodate these challenges. But again, as I was telling, right, running multi-region is last of your option when you're running in Kubernetes. So here is a sample architecture that we wanted to share in terms of multi-region, multiple Kubernetes cluster. So you see here, we have two Kubernetes clusters. One is running in a region A. The second one is running in a region B. We are having a dedicated ALB across each region, one of our routing patterns that we saw. And then we can use Global Accelerator. Let's talk about Global Accelerator. So Global Accelerator has some rich set of features that which you can use to enhance your traffic routing across multiple clusters. So Global Accelerator has features like geo-based routing. It has latency-based routing. It has active-active routing. It has active-passive routing. So which means you can use Global Accelerator as a mechanism to use according to your organizational disaster recovery or your organizational multi-region needs. So with this approach, a sample approach, you can still achieve multi-region in AWS. All right, next, let's talk about some of the strategies with respect to databases and storage, because I was talking about the fundamental challenges, how we are going to manage the data replication and database replication lag, right? So we'll talk about some strategies that you can use to mitigate those challenges. First and foremost is, let's say you're running a container workload, and you have an opportunity to refactor your workload to use a NoSQL database. So then in that case, we highly recommend something like Amazon DynamoDB Global Table. The biggest advantage of using Amazon DynamoDB Global Table is, with this approach, you can write to multiple write endpoints, and you can also read from multiple endpoints across different regions. So which means that you can mitigate the risk of the lag that you're going to get in terms of your database usage. So, I mean, of course, Amazon DynamoDB Global Tables is feature rich, and you can read about it, but using this approach is definitely going to help you mitigate some of the database replication lag issues. But let's say your container workload is pretty monolith and you can't refactor to use a NoSQL database, right? Then you can still use something like Amazon RDS cross-region. We have seen customers choosing this approach. It's just because they get that opportunity to run cross-region. So take this example, right? You have a primary database, a primary writer RDS database in a single region, and you're having read replicas in other regions. Let's say you're running two regions, you're going to have read replicas in another region. So the reading happens from read endpoint, the writing happens to a writer endpoint in one region. But what if there is a regional failure? So what you can do in this situation is, you can promote your read replica to a primary in the second region, and you can still continue your operation. But one caveat that we need to remember, or one operational aspect that we need to remember here is, promotion of a read replica into a primary is not automatic, which means you need to do a manual process or some kind of SOP, like standard operating procedure process in your organization, to make sure the replica is promoted to primary. Another important thing you need to understand, or you need to think about while architecting this approach is, let's say your application parts are using writer database in one region. After you promote a read replica to a primary region, you need to re-update those endpoints into your application parts and maybe restart your parts so that it points to the right database after the failover. So these are some of the architectural aspects you need to think through when you are using this as an approach. But again, this is definitely a good approach to mitigate the database replication lag issue that I was pointing about. Next, let's talk about, we talked about database, let's talk about data. Let's say your container workloads are using storage, like persistent volumes for running the stateful workloads. So one of the, we have seen customers using one best approach is using EBS. Why EBS is just because you can back EBS directly to your container persistent volumes. You can use EBS to take snapshots, and you can also take incremental snapshots. That's the key point here. You don't need to take snapshots every hour with full backup. You can take incremental snapshots. And another important thing is you can do a cross-region copy. So let's say you are having an active-passive pattern, you have a backup and recovery in a secondary region. You can use this approach, you can do some automation to copy your persistent volume data periodically to the secondary region and be standstill and ready for a disaster. So this is one approach we highly recommend to customers, and we can also, there is another approach called EFS. You can also use EFS as a backup option, or EFS as an option for a persistent volume. So these approaches can mitigate these data replication issues that I was talking about from the challenge standpoint. All right, so we talked about database strategies, we talked about data strategies. Another important thing is we need to also account for container images, right? Because container images are core for running your workloads in a secondary region if you're running active passive. So primarily what, in the olden days, like a few years ago, what we do is we use a pipeline, like a code pipeline, we build the ECR, push the image to, we build the image, we push it to ECR, and we will have to run another step, which is basically an extra step to copy the image or create the container image in the secondary region as well to be prepared for disaster recovery. But with this particular feature that we have announced, which is basically called CRR, which is cross-region replication, we have seen customers taking good use of this feature. They can totally avoid the overhead of copying the image to a secondary region. So which means that whenever a container image is created in ECR in one region, the CRR will take care of copying the image to the other region. So which means that you are all ready to run your workload in a secondary region as soon as there is a disaster. So this is another approach we can take. To sum it up from a multi-region standpoint, so we saw both challenges and we saw some mechanisms to mitigate these issues from a multi-region standpoint, but still we highly recommend that unless it's a mission critical situation or a situation where we have to run in two regions, we highly recommend not to run in a multi-region as a close-up. I'll hand it over to Ray to sum it up.
Thank you. So I think I just want to quickly recap so you can congratulate yourself if you're already using Kubernetes that you're almost halfway there to be able to run your applications in a very, very resilient and reliable manner. Kubernetes is in itself designed to be self-healing, and it provides your applications a way you can automate self-healing, you can automate scaling, and we highly recommend that you actually use some of those features to make sure that your applications are very, very responsive to scaling and responsive to outages within the application itself. And then EKS really provides you this cluster, which is production grade, in which you don't have to worry about the availability of the control plane itself. We saw in the last session how we're continuously using learnings from operating millions of nodes and condensing them into best practices that we use to deploy the cluster control plane. So if you're using EKS, your focus is primarily on your workloads, and you don't have to worry about the availability or the stability of your cluster itself. And then we saw how some customers are considering going multi-cluster just to eliminate the cluster itself as a single point of failure. I think we're going to see that trend increasingly as operating multi-clusters becomes easier. So if you are worried about control plane as a single point of failure, here are some strategies that we shared that you can use to manage multiple clusters and deploy your applications across multiple clusters, which some of those are GitOps, which I highly recommend. Even if you're doing single cluster, you should really consider using GitOps. But if you're doing multi-cluster, then without doing GitOps, it's just impractical. You're setting yourself up for failure if you don't use GitOps with multiple clusters. And then we also talked about some of the networking services, so how you can take that traffic and spread it across multiple clusters within a region, and then also across multiple regions. But the key takeaway that I want to say is that a lot of customers come to us and say, I want to operate in multi-region, without fully understanding how big of an undertaking that is. And it is really big, because you don't just have to think about Kubernetes. Running a stateless workload across multiple regions in Kubernetes is super easy. You can do it without any problems. But running a production-grade application that has data, that uses databases, that has persistent volumes, is going to be hard, because you need to make sure both the regions are in sync. So the way to think about it is, if you're thinking about high availability, if you're thinking about fault tolerance, you're thinking single region. If you're thinking about disaster recovery or global deployments, only then, for the most mission-critical applications, you might consider multi-region. But there are challenges that you'll have to overcome in that scenario. I want to leave you with some resources. So a lot of what we talked about is documented in the EKS Best Practices Guide. We have tons to say. I can spend the entire day talking about EKS best practices, but we only have 30 minutes. So I highly encourage, if you thought this was useful, go read the EKS Best Practices Guide. It's available on GitHub. It's an open source project, and you can read all about what AWS recommends in terms of running Kubernetes clusters there. And then we also have some learning resources, some workshops. So EKS workshop is really helpful if you want to familiarize yourself with operating EKS clusters. You can use these hands-on lab to learn about a variety of things like deployments, observability, using GitOps, using Helm. So a very good resource. And then we talked about fault injection simulator. So we have a chaos engineering workshop that you can use to get started if you wanted to test the resilience of your cluster. And also we have a SaaS workshop available, which is really designed for SaaS people, but it is also very, very helpful if you want to understand how to operate multi-tenant clusters at scale. So some really good learning resources. The EKS roadmap is available on GitHub. So if you already haven't seen it, I encourage you go and see what is coming. What is the community asking for, and you can add your voice there if there's a feature that you'd like to recommend, or if there is a problem with EKS, you can use that mechanism to communicate with the EKS product team. And then the containers blog, I recommend that you subscribe to that. It's where we announce all our new service updates, and we share our architecture patterns. So that's about it. Thank you for attending our session. I think the next session is right after that. Awesome. All right. Thank you, everyone.